hear me say it earlier, I've actually typed this up. It's with the test 4 notes. It just says test 4 review summary, and it details the same thing as here. It's just a little bit prettier than this handwritten Jabberwocky. Line integrals, 2 types. You know, I will put one of the ds type and one of the dxdy type. In both cases, I mean, they're evaluated differently, but if you have one of the ds types, it's the one where you have to use that square root expression to accommodate the arc length of your curve. So, like on this one here, number 3a, you'd actually, I think we may have done this one in class. Sorry for the redundancy if we did. You always replace x and y with their parametric counterparts. So your integrand is going to be x, which would be t squared, times y, which is 2t. So that's contributing part of your integrand right there, just 2t to the third. Okay, just making those literal replacements for x and y. ds. Anybody recall what ds gets replaced with?
The square root of x prime squared plus y prime squared.
Yes, it's essentially the parametric equation version of arc length to accommodate the actual curve that you're integrating with respect to. So yes, the square root of x prime, and again, everything in terms of t, so x prime is 2t, that'll become a 4t squared when you evaluate that. And then y prime is just 2, will become a plus 4. And that's what your integrand becomes. What are the limits going to always be?
0 to 1.
Well, in this case, 0 to 1. More generally, they're always going to be the t values that go along with your parametric curve. So in this case, they're 0 to 1. And then that should turn into something you can probably integrate. That's going to be, oh, this is one of those funky u-subs. This becomes 4t squared plus 4 inside. And then you have a 2t to the third on the outside. Yeah, that's one of those fun u-subs. You know what I'm talking about?
Mm-hmm.
Oh, please show me.
You gotta
Oh, where
work the
you said it
x.
was t.
Yes.
You put it in terms of t.
Yeah, you've got 2. Yeah, you got 2t to the third, square root of 4t squared plus 4. And so, yeah, if you notice it and you want to take the liberty, you can factor the 4 out of the radical if you so choose. Do I have? Oh, there we go. Here's the one that's got a link in it. So yeah, and I think if you don't mind, I am going to do that. If you factor that 4 out, here's the 2 that was there to begin with, and here's the 2 that comes from factoring of the 4. So I've got the t cubed there, and this is t squared plus 1 to the half. So, yeah, this is one of those less than obvious u-sub tricks. I may not be too terribly mean like this on the test, though. But it's good to expose you to it, just because, you know, hey, it's pretty cool. U equals t squared plus 1. Unfortunately, du's only requirement is a linear 2t with dt. So, I'm going to borrow one of these 2's, I'm going to borrow one of these t's, and pair with my dt. Okay, so sorry about the sloppy mess there, but all that, you know, funky little sideways, upside down letter E shape, that's all my du. I've still got this extra 2 in the front. Am I losing anybody? Are you with me? Are you with me? Are you with me? I had a teacher who'd ask that all the time. That's the way she pretty much punctuated her sentences. Are you with me? Are you with me? Very good. Okay. And then, so yeah, the 2, the t to the first, and dt become du. This becomes what you want, u to the 1/2. So I'm giving myself way more space than I need here. But then, there's this extra t squared that doesn't fit with our fudging. Doesn't fit with the whole u sub manipulation. But
U minus 1.
replace t squared with u minus 1. Because the u sub is just that versatile. You can use this equation in multiple ways. So that standalone t squared, bada boom, bada bing, gets replaced by that. And the trade-off is, this algebra is a lot more manageable. You're integrating u to the 3/2 minus u to the 1/2, which is just a couple of power rule applications. Okay. But the big picture here is, sorry to get you, lost in the minutia of a clever u-sub. ds types of line integrals, take your parametric curve, replace x and y. The ds differential from the original problem is that square root of x prime squared plus y prime squared. Yes, sir.
Can we put t to the 6th under the radical?
Can we put t to the 6th under the radical? You mean introduce this in here?
No, up 1.
Up 1.
Oh, yeah, sorry. Yeah.
So if you, but see, so if you brought the t squared in as a t to the fourth, then that becomes t to the sixth plus t to the fourth. But you still have this linear t on the outside. I think that's making it more
The
difficult.
step above it.
The step above it. So you want to bring this inside.
Yeah.
Well, see, if I want to reverse the chain rule, I'm going to want to let that be my u, and then the derivative of the inner function needs to be something out here that I can pair with my dt.
Yeah, because your du would be weird.
Yeah, your d. If you brought that in, you'd have to first off square this to t to the sixth, multiply it as t to the eighth plus t to the sixth, with the fours in there or not, and then your u commits to all that. But then there's nothing on the outside to pair with dt for your du. So I think this one was kind of reverse engineered, to use this particular u sub trick. Okay, and then QED. I know you're sick of that, and no, you can't say QED on the test. All right.
But you know the material.
I know the material. You're the one who's learning for the first time, so demonstrate. All right. So, for QED, that which will be demonstrated is what yours will stand for on the test. All right. Not which has been demonstrated. Okay. DS type, dx dy type. Sometimes you see just one differential, dx or dy. Sometimes it brings dx dy dz in the mix like this. So that's what I mean by the dx dy dz type. You'll be given a parametric curve, sometimes in 2D, sometimes in 3D. Oh, and look, sometimes you have to come up with the parametric curve yourself. How do you parameterize this arc that's mentioned in 4a right here? The curve C is the arc that goes along the square root y equals square root of x curve from the point 1, to the point 4, 2.
X is equal to 2.
Yeah, it's that same kind of, well, I hate to call it jippy, but it's kind of like a jippy parameterization. If you have but it works. If you have y equaling a function of x, always default t to pairing with x. And then since y equals the square root of x here, and x equals t, your y curve would be the square root of t. So there was one like that on your test 1, I think, where you had to parameterize a y equals ln or e to x cubed or something. Same idea. If you have y equals a function of x, always let x be t, and y would equal that same function just in terms of t versus x. And then what would your t limits be here? Yeah, t equals x. So good thing you got those points. The x value 1 to the x value 4 would dictate the t value 1 to the t value 4. How would you parameterize, well, we've done line segments. How would you parameterize this line segment in part D? And again, the prepositions kind of give you another locative. You're going from this point 1, 0, 0 to this point 4, 1, 2.
Like 1 to 4, 0 to 1, 0 to 2.
Okay.
T is,
Well, there's two things you need to find any parametric set of equations for a line.
you need an equation.
You need a point. You got a pair of points, and there's one that's more convenient than the other to use. Well, no. In this case, in this context, there is one that you have to use as your beginning point. You're going from this point to this one. So this has to be your beginning point, and whatever your beginning point is for your parametric triplet, that represents the constant terms for your parametric equations. Then you have some coefficients of t. Where do those coefficients of t come
3,
from?
1, and 2.
The direction vector. A direction vector into and you gave me 3, 1, 2. So I think that's what you said.
Yes.
Yeah. So the direction vector is always best if you take the end point as the head and the beginning point as the tail. So head minus tail here would give you the direction vector 3, 1, 2. So then that becomes your t coefficients. And if, and only if, you use the vector that connects beginning point to end point, what is that always going to guarantee your t limits to be? 0 to 1. Because essentially you're starting from this x, y, z location in space, and you're adding those components to x, y, z respectively, one copy of those components. And so 1 plus 3 takes you to 4, 0 plus 1 takes you to 1, 0 plus 2 takes you to 2. So if you use that unique direction vector that goes from tail to head on your 2 points, then that'll always guarantee 0 to 1 for your t limits. Okay? Or the parametric equation could be given. Okay. But the difference is, in this particular type of line integral, there's a lot of overlap, but it works differently. You don't have the ds differential, so you don't need that square root of arc length expression involved in your integral. You just replace every x, y, and z with their parametric equations. That's consistent all the way across the board in every line interval. Take the parametric equations and they become your literal replacements for the letters x, y, and z. But what about the differentials dx, dy, dz? What do they get replaced with? Well, eventually dt. But for example, in this one, what would dx be replaced with if I'm using this parametric curve? 3 dt. The derivative of x would be 3 times dt. dy would be replaced with dt. dz would be replaced with 2 dt. On this one, where you see a dz on part C would be replaced with 2t dt. So the d parts are always the derivatives from parametric curves. So everything comes from the parametric curves in these types. The verbatim replacements for x, y, and z here, along with the derivatives of x, y, and z, paired correctly. Yes, sir?
Why is it not just 1 for the y? Why
It's-
is it dt?
No, because you're essentially wanting x, y, and z to be replaced with an integral in terms of t. So if I make these replacements right off the bat, this first part will become 2t squared, because that's what z equals, and z is squared. dx becomes 3 dt. So when you make these replacements, you'll have 3 different dt's in there that you can technically factor out, and then whatever's between the integral and the dt that you factor out is really what you want to integrate. And then x squared dy, after the plus sign, would become 1 plus 3t squared. dy is just 1 dt. And then the final pair right here, y squared, would become t squared times dz, which is 2 dt. And so that's what you're going to integrate. And even though it looks funky with these dt's thrown in the mix, you can factor 1 dt out all the way to the right. So it's actually going to be 12t squared plus, you can FOIL that. So that's what you're integrating, and then you just have 1 dt necessary on the right from all these expressions that you factored dt out from. And then what are your limits?
0.
Yeah, 0 to 1. The t values that define your curve are the t values that go in your integral. And then just carefully integrate your polynomial. Plug in that 1. And the reason 0 to 1 are handy limits, especially on polynomials, is you can technically go straight to the answer. See, if you integrate this, you're going to get a coefficient of divided by 3, so you get 4t to the third, and t to the third is eventually going to replace with 1. So when you have 0 to 1 on a polynomial, it's really just the coefficients. That becomes a t, so 1t. That becomes a 3t squared. That becomes a 3t to the third. And that becomes a 2/3 t to the third. And then when you plug in 0, everything wipes out. So it's just kind of a handy shortcut. But again, it's limited. It's only 0 to 1 for polynomials. Yes, sir?
So why is it that t goes from 0 to 1?
Oh,
In
because
this particular case?
in this case, since we use the only vector that connects this tail to that head, the 2 points that we were that defined our curve C, then if you use that unique vector that goes from here as the tail to there as the head, that's always going to be 0 to 1. I mean, think about this saying. Think about t as your. I mean, it's your parameter, but it's essentially saying I'm going to add 1 copy of this vector x, y, z to this point x, y, z. So if I add 1 copy of those x, y, I, j, k components to that, it takes me 1 plus 3 to 4, 0 plus 1 to 1, and 0 plus 2 to 2. So that's why you can get away with 0 to 1, because it'll take you linearly from that first point to that second point by using 1 copy of that vector's components. Yeah.
It's not like a unit vector.
No, it's not a unit vector. This doesn't mean that it's a unit vector. That just means that you're adding 1 copy of those complete set of components to these in tandem to take you to those points. So yeah, that doesn't mean it's a unit vector. It just means it's 1 copy of the vector that you're adding to here to get to there. I mean, you could use the vector, the direction vector 3/2, 1/2, and 1. But then what are you committing to here? If you cut that vector in half, your t limits go to what?
0 to 2.
0 to 2, because you need to add 2 copies of that vector, go from 1, 1, 0, or 1, 0, 0 to the other point. You see? So any vector that's parallel to this will suffice. But the most convenient one is just the vector that goes from here as the tail to there is the head, because there's the sweep limits. Okay? Oh, there's somebody's lunch.
It's in there.
Okay, there's somebody's daughter. All right. That's always scary. Sound of Well, I mean, it's a pretty girl, but I mean, just, you know, you got a picture of your daughter out there for everybody to see. So, we're the creeps out there. Just being mindful of the creepy folks. Not that I'm creepy, just, you know, it would scare me to know that it's a picture of my daughter floating around somebody's lunchbox. So, the other type of line integral, I digress, with the fundamental theorem of line integrals and conservative vector fields. So I'm tying that in with your example of an f dot dr line integral. Okay, the fundamental theorem of line integrals and Green's theorem, one problem for each. First things first, before we get to the FTLI, you need to make sure you're aware of what a conservative vector field is. A vector field's conservative if it represents the gradient of some scalar function, little f. In other words, there's some little f function out there such that when I take its gradient, it gives me these components from its gradient. Okay. There was a test that I mentioned. There's a way to test a vector field to see if it's conservative or not. Research that, because I know it. You're going to be tested on it. So do a little digging. How do you test a two-component vector field for conservativity? It involved calling this first component P and this component Q. And there's something you do with those P's and Q's to check for conservativity in two dimensions.
If the two
You
partials
check
are
if
equal.
P and Q are equal.
If something involving partials,
You take
If the partial of P is equal to the partial of Q, then there's exactly.
okay, but give me a with respect to.
Partial P with
Py
respect
is equal to QX.
Yes, P's partial with Y has to equal Q's partial with X.
That means they're
Because
exact.
remember, if this is already a function's gradient, this is the first partial with respect to X, and this is its first partial with respect to Y. So if you go to the second mixed partials and take this partial with Y and this partial with X, those have to equal each other if this came from a gradient. So that's the check for 2D. P's partial with respect to Y gives me e to the x cosine Y. Okay, you all right? I thought you were about to shoot me with a rubber band or something. Okay, partial here with Y, e to the x cosine Y. The partial here with respect to X is e to the x cosine Y. So that one is conservative, okay? Once you determine it's conservative, how do you get the potential function?
Isn't that where you have like the function of X and the function of Y?
You want to do the gradient backwards. You establish that this is a gradient, which means this is already the partial with respect to X for some little function f, and this little function f, its partial with respect to y, is this e to the x cosine y.
Is this what you call the anti-gradient thing?
This is, yeah, taking the anti-gradient to help you create the original function. So if this is the partial with respect to x, what would that have had to have come from the original function? What do you have to do going from here to the function? Yeah, undo this, integrate with respect to x. So if I integrate here with respect to x, okay, that's going to take me to e to the x, sine y is a constant. And remember, there's one little tiny technicality you need to remember. Instead of plus c, plus some function that would have only depended on y, okay? And since we're calling the parent function the potential function f, I usually use g's and h's. So there could have been some g of y that would have been here that got annihilated when you do that partial with x and go back to this. Same idea, you want to integrate the q component with respect to y, which in this case you're integrating cosine y, which conveniently leaves e to the x constant, and cosine y goes to positive sine y, no sign change. And again, since this was an integral with respect to y, there could have been some function that only depended on x here. But according to these two partial antiderivatives, either one of these statements represents your original potential function. According to this, the original potential function should be e to the x sine y, and then what is this g of y function according to this? 0. If you don't see a standalone function of y here to represent that g with, and vice versa, if you don't see a standalone function of x here to represent that h guy, then that is the only contribution for your potential function. So the potential function is e to the x sine y. Okay. Now here's the beauty of the FTLI, the fundamental theorem of line integrals. If you're evaluating one of these f dot dr line integrals through a conservative vector field, the long way of doing it is to go back to what we did previously. You need your parametric equations. Replace every x with its t equation, every y with its t equation. dr represents the derivative of your parametric curves. You build that dot product, it's in terms of t. Your t limits define the limits on the integral, and so it's a construction process. But if I had this original vector field here in part A, did I copy that correctly? No, I didn't. Sorry about that. And I want to evaluate this line integral along this path. Let's see. With that orientation. Okay. What does the FTLI tell me that I need to do to evaluate that line integral along that path?
Draw a line.
Well, no. Okay, if I draw a line, okay, so you're committing to a new line integral, but, so what's the value of it going to be? Look it up in your notes. I know the answer. Dig. You're going to need to be able to dig on Tuesday, so dig. Find it. The notes on FTLI, what does it tell you to do when you're evaluating an f dot dr line integral through a conservative vector field? Oh. I'm going to get your test back. Okay. Anybody else not get their test back yet?
Today?
No, if you took it after 12, you were in there taking it when I picked them up. So, yeah, I haven't got yours yet.
Like, if we took it this
If
morning.
you took it after 12, if you took it this morning, I've got it. You're
Yes.
Matt
Love.
Love.
Yeah.
And you're Chris. Okay. Schaefer.
Yep.
It improved. Nope, Matt. Sorry.
I can barely contain my happiness right
Okay, we just contain it to the end of class. Okay. All right. So, have you found what you need to do here to evaluate that f dot dr line? I mentioned the words path and dependence when dealing with these line integrals. Yes.
I mean, this is just a conjecture, exactly, is it just like you take your function and you multiply it by the distance?
No. What do you do? The first time you heard fundamental theorem was most likely with calculus 2.
You
take
plug
an
your last
antiderivative
point into
into
the potential function.
yes, you got the
And
name
then-
right and everything.
And then subtract your initial point plugged into your potential function.
Yes, it's pretty much the line integral analog of Calc 2's fundamental theorem.
Yeah.
Where in that case it was antiderivative, plug the top limit in first, or your rightmost limit in first, and then minus your leftmost limit plugged into your antiderivative. In this case, instead of antiderivative, it's this anti-gradient function. Proper name is the potential function. So this line integral equals the potential function. Again, it's I'm trying to be very emphatic. You can tell it in typed text, but my written text may be sloppier. Capital F is the vector field, but little f is the potential function that we get by doing this gradient reversal from the vector field. So now it's a scalar function, and you evaluate the scalar function at your endpoint minus the scalar function evaluated at your beginning point. And so since that is our potential function, e to the x sine of y, we would have e to the, your endpoint first. There's our endpoint. What tells you that's the endpoint? Orientation, baby. Yes, those arrows let you know. You began here at the origin, you stopped at 2, pi over 2. So endpoint plugged in first. E to the x, so e to the 2 times the sine of pi over 2 for x and y, and then minus same potential function evaluated at 0 and 0, which e to the 0 times sine 0. Sine's going to wipe that one out. That's a minus. It's a very long minus, but this minus this leaves you with just e squared. Oh, well, yeah, e squared. That's it. Ta-da! So no matter what path you take, the straight line between those points, a crazy curve like this, a spiral that ends up at 2, pi over 2, any path you take from here to here, this work integral, this f dot dr integral is always going to be the same value of e squared.
So, can you run through the steps of determining whether it is a conservative interval?
Okay, you want to, for 2D, if this is, if you go into this with the assumption that this is already a gradient, then that means this is already, sorry for the glare, this guy's already a first partial with respect to x. This guy, this gal, whatever gender it is, that's already a first partial with respect to x. This j component is already a first partial with respect to y, because that is how you do the gradient. You take the original function f, partial with x is the I component, partial with y is the j component. So if that's what you're going in with the assumption of, and you want to verify it's truly from a function f like this, take this, thing's partial with respect to y, and then take this thing's partial with respect to x. And for any kind of scalar function we have in this class, these second mixed partials are always going to be what? Equal. F's, and that was the trick on one of the test 3 problems. That first problem where you're at, that second problem where you're asked to do f, x, y, and f's first partial with x is a big hot mess because you have this big old crazy secant ln quotient function in terms of x, but then the second partial was y, which would annihilate it. So if you did the other order first, if you did partial with y first, that freaky x thing is gone. So these are always going to be equal. So since that's true for any of our scalar functions, if that's already first partial x and first partial y, take this thing's partial with y, this thing's partial with x, and if those are equal, then that is indeed some function's gradient. That means this is a conservative vector field. And then any line integral you evaluate can be found by using its potential function evaluated at the end point minus potential at the beginning point. Okay. So the way these, you know, sometimes you see them in textbooks where the, let's see, the curve might be some kind of crazy curve like this. You know, this is, I guess, an extreme graphic example of the same thing I did on the board here. The figure here shows members of the vector field y squared I plus 2xyj with 3 different paths connecting the point 1, 2 to the point 4, 3 right here. Okay, so and they all are pretty much going from left to right. This guy snakes a little bit left and then goes back to its rightward path, but they're all connecting the same beginning and ending point. So you're asked to explain why is f dot dr's line integral the same value for all 3 curves.
Network is the same.
Well, why would the network be the same though? There's really only one unique answer here.
FTLI.
And that comes from a conservative vector field because the vector field f is conservative. Partial here with respect to y is 2y. Partial there with respect to x is 2y. So because it's conservative, that's true. Okay. And then it asks you to evaluate it. What would any one of those 3 line integrals values be? Let me see if you can get that potential function just by looking at it. It's not too tough. What would your potential function be for this conservative vector field? He hesitates. He hesitates.
Yes, xy squared.
Back to his consultant. Yes. xy squared. Integrate that with respect to x. xy squared. Maybe a g of y there. Integrate that with respect to y. x y squared. So you get the same thing in both cases. So your g of y here and your h of x there are zeros. So the potential function here should be xy squared. So you're almost done. What's the actual integrals value? 14. Oh gosh, it's quick. So let me do it too. This is the point 4, 3. So x 4 y squared is 4 times 9, 36 less.
Never mind.
Well,
I thought that said 2 on the x-axis.
oh, so yeah. Double check that. So the end point is 4, 3. So xy squared evaluated at 4 and 3 would be 4 times 9 is 36 minus xy squared evaluated here would be 4. So it should be 32. Yeah, any one of those 3 line integrals because of the path independence, which comes from the vector field being conservative. Okay. All right. So that's what the FTLI and conservative vector fields are all about. Green's theorem has its own problem set. This is on page. All these problems relate to Green's theorem on this page after that. What did Green's theorem allow you to do for line intervals on looped curves? Look it up. You're gonna need to Tuesday night. Know your resources. Know where to find it.
Counterclockwise.
Okay, the orientation of the curve should be counterclockwise to use the original form of Green's theorem. But the main gist is, what does Green's theorem transform the line integral into?
Area.
A double integral.
A double integral over what region?
3D.
2D region enclosed by the curves.
The 2D region enclosed by the curves. Very well recited. Yes. So, Green's but see, that's the thing. That's the gist. He knows where to find it. All of you need to be held to the same standard. You just know where to find it on Tuesday night, and you'll be bulletproof. So, but the essence is, don't forget what was also mentioned. Green's theorem, in order for you to turn it into that double integral, it has to be a curve with counterclockwise orientation. So, this curve right here, this one's given as a graph, and that is counterclockwise orientation. So what that means is, if you use Green's theorem here, well, actually, this first problem wants you to do the long way and the Green's theorem way. Because remember, how would you have to do this the long way? Remember the square? One over all three different curves. A line integral here, essentially a dx dy type of line integral. So you got to parameterize that, plug, evaluate, boom. And then parameterize this, plug, evaluate, boom. Parameterize that, plug, evaluate, boom. You have three different line integrals. Versus Green's theorem, which lets you turn this into a double integral over this enclosed region here. So you still need to know the equation of the curves, okay? And the other thing is, what does your integrand become? Green's theorem does turn a line integral into a double integral, but what is the integrand inside here based on?
Q of x minus p to y.
Okay, and so tell me,
Or that's the partial integral of x.
partial derivative.
Partial derivative.
Yeah, that subscripts mean, those subscripts mean derivatives. So up here in this original line integral for part B, who is playing the role of P?
X squared, y squared.
Yeah, it's alphabetical order every single time. P is paired with the dx differential, and Q is paired with the dy differential. So Green's theorem's integrand is double integral of Q partial x minus P partial y, integrating over the 2D region inside the curves. So if you set this up, Q's partial with respect to x is just y, minus P's partial with respect to y is 2x squared y. And then what order of integration would you want to commit to? Because I haven't listed dy dx or dx dy yet. Why and why?
Oh, because
You already have the y.
this is y equals x squared.
Because it's a curve defined as y being a function of x. It's in a y equals form. So just to take care of that convenience and avoid an x equals square root of y, the y's limits, bottom to top, y goes from y equals x squared to, right there, y equals 1. So those would be your y limits. For some reason, they're a little bit bigger than usual. And then x, when the y dimension is done, flatten the entire space to the x-axis. And even though it doesn't come in contact with the x-axis, don't let that fool you. If this is flattened to the x-axis, you would have an interval smudged between 0 and 1. So you diminish it down to that last dimension, that single dimension x, and that should be your limits. Unfortunately, this isn't constant limits, so you can't do the factor and split